Hello everyone and welcome to the Victoria Game Engine series. This is episode 7 and today we are going to be looking at the platform layer, OS class and display manager. So before we actually get into the nitty gritty of what those classes will do, we are going to just go over and do some very quick cleanup and some modifications to our files that we need to do in order to make most of this video possible. The first one I'm going to do is something that I was kind of umming and ahhing about through a lot of the development of the series and through some of the actual creation of it, and I've just decided to go ahead and do it. And that is going to be the changing of many of our if and defs defines into just pragma onces. And it's literally just down to me being lazy. So we're just going to go and we're going to do pragma once. And we're going to get rid of the end diffs in every file, and we're going to go through and we're going to be modifying pretty much every single file in this way. Alrighty then, so that's all of our files now all pragmaed up. And that was the only real change that we needed to make in terms of just header file stuff. The next change that we are going to do, as I close everything else because I won't need these for now. So as we can see in our logger file, we are going to be doing some changes. The first thing that we're going to be doing is we're actually going to be getting rid of this singleton. And we're going to be getting rid of the get singleton message. We're going to keep our max buffer length and we're going to keep our this. But we are going to change something as well. We're going to include stdarg.h. And we are going to change some of the definitions that we use now. We're going to be using VA list here, which technically I don't really want to be having stdarg in such an important file. But since we need this because the built-in VA list won't work for every single compiler, even though it will work for using Clang and GCC, we want to be using this version so that we can maintain just a consistent compatibility, and also because I don't want to have to keep writing built-in VA list because it will get confused with the actual VA list, and that's a whole route that we don't want to go down. The other thing that we're going to do is we're actually going to be getting rid of all these print macros. I did mention, I believe in the last video, that we would be doing this. That is simply because the way that we'll now deal with our printing is it will now be going through our OS class, and I'll get onto that a little bit later. So we've marked this method logv as being virtual, and the reason behind this is because we're going to have classes that inherit from logger, and they're going to want their own versions of being able to log things, which is why we've got it in this setup this way. As a base logger, we still want to keep it as the absolute most basic function of being able to print to the console, but we now want it to also be able to be overridden so that we can customize it on different operating systems. We can have loggers that log to files, and so on and so forth. So there are a lot more things that we can do. We're also going to be writing a virtual function here that is just log error. And it's going to take a bunch of arguments that I'm just going to grab from here. And you'll also see that we now have a error type, and that is because I have forgotten to add an enum. So we're going to create the enum error type. It's going to have error ERR, error warning, error debug, and error shader. So log error will take the arguments of the file, the function, the line, the error message and its details, and the type of error it is, much like we get in our error macros here. And effectively what we're going to be doing is we're going to be replacing wherever these go to, which is log f. We will be replacing it with log error. But that will be a problem that we can sort later. And the error type, this will simply just change how it prints things. So if it's an error, if it's warning, if it's debug, or if it's a shader, it will print things to the console differently. And unfortunately, the log debug method is now going to be going, since it's superseded by log error having the option of using debug anyway. We can just safely get rid of it. And we also And that just means that we're now left with simply 3 methods within our logger class as a base. Now, we do have some problems here in our C++ file. Of course, we don't have a singleton anymore, so we can get rid of that. We can also get rid of the class constructor there, because that's also gone. The other problem that we now have is that we don't need... Oh, the other thing that we can now get rid of is our log debug. That can go. That's now gone. And we're now left with simply converting this to a VA list of type arg pointer. I believe if I mentioned that there, we want to rename VA list, instead of being built-in VA list, we want to rename it to arg pointer. And that just means going through and changing wherever that is specified there. And because we're using stdarg here as well, we can use that as a VA list there. And we can probably just get rid of that include there because we already have it set here, and that'll just be an unnecessary extra include. Next thing that we're going to do is we're going to specify here where we want to print our method to. So we're going to change this to fprintf, and here it will reference stdout and stderror as the 2 main places. Stdout is normally where printf goes to, but in this case we want to specify where we want that to go, and that will depend on if it's an error or not. So we're going to do is error, and if it's true, then we want to print to stderror. Otherwise, we want to print to stdout. Another thing to note is that for this, the reason that we use stderror here, the difference between stderror and stdout is that stderror will print a error message more rapidly to the console than an stdout message does. Because the idea is that because it's an immediate error, you need to have this forwarded to you immediately. So whereas with stdout, it can wait in the stack for a little bit longer before it gets printed. So the next thing to do is to define our log error function. And the way we're going to be doing that is we're going to be going void logger log error and get our same list of macros here. For these basic error strings, or for the error printing, we're going to be, of course, going to log f because we need to format certain things about them. And the way we're going to be doing this is by first off having a bunch of error strings to define all of the different error types that we can have, as you can tell by our lovely error type here. If you're wondering if this is any different to the error types that we have set in here, they're not. These are simply the different error messages that we can then pass into a actual string. In this case, we're simply talking about the error types that we have defined in this enum here rather than the error enum here. They're 2 separate things. It might get a little bit confusing, but hopefully that makes sense. So here we're going to have a const, static const char of error strings, and they're going to equal error, warning, debug, shader error. And you want to make sure that this is a closed bracket here, and you can set that to 4 so that it can specify. And here we set this to being a static list of strings, so that way we're not creating this array of strings every time we call this function if we don't have a higher logger set up. And these will just be saved in memory as a permanent address that we can keep referencing when we need them. So then we make our calls to log f. Of course, we're going to need to set it to true because this is actually an error that we need to pass to the console. We're going to have the format here be %s, 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 \n. And then we're going to want to get from our error strings of type. Because type is an enum here, it should be able to access the error strings like an integer. So it's set 0, 1, 2, 3. So it will access 0, 1, 2, and 3. And these are the same. So then we actually want to get our message that we're trying to send to the console, which is set to error message and error details. And then we want to submit another thing, which is the new line. And this is just going to tell us where the error message is coming from. So we'll have the function that it's coming from, and I'll have %s, %i, and a new line of function, file, line. Actually, I changed my mind. We're going to do it file function line. So that way it's printed that we have the file that it's coming from, the function that's being called, and the line number that we have. And this is just my personal preference. And with that all done, that's our base logger class now all tidied up and ready for what we're going to be doing next. Before we actually get into any code, I need to explain what the platform layer is and why it's significant to what we're doing today. So as many of you will know, not every function that we want to call will work the same or act the same on different implementations of the operating system. That's evident from the fact that we have separate make files for Linux and Windows, because they compile fundamentally differently. And this goes the same for a lot of the code we need to write for getting a triangle to render on screen, which is our current goal. For instance, using the API for Windows to create a window is very different to using the APIs, plural, that exist on Linux to create a window. However, because we want to make sure that every version of the application runs the same, regardless of what device you're using, we're going to need a way to take all of that nitty-gritty direct interference with the operating system's API and put it to a higher level that every user can call, but depending on what operating system the application was compiled for, will change how the application runs. This will be a theme that is very prevalent throughout a lot of the next few episodes that we're going to be doing, because we're going to be spending a lot of time writing an implementation for Windows, and then we'll be writing an implementation for Linux. However, for now, I need to explain the more arbitrary parts of our code, and that is our base classes that we're going to be then extending in this implementation. With that all said and done, this is finally where the OS part of our core comes in, and that's where we're going to be writing os.h. And that's, again, going to be pragma once. We're going to include our core and type defs. We're going to want to include core-data-event. So once you've included those, we're going to be writing the class OS, and we're going to be opening these brackets. The very first thing that this class is going to have a section called the protected variables. If you remember from when we were talking about the different class structures, we have three main variable types: public, private, protected. Public and private, you hopefully understand by now because we've used them fairly extensively throughout the series. However, at this point, it's important to be writing to understand what protected does. Protected variables essentially act very similarly to private variables. Outside interference cannot change these different variables within the class. However, extensions of this class can change these variables and use them as well. And this is going to be very useful for later implementations. Another thing I forgot to include, because we actually even though we spent most of the first part of the video doing this, is that we're going to need to include core-io-logger, because we're going to be using our logging class in just a second. The first thing we're going to want in this class is we're going to static os pointer singleton. I've explained singletons a fair amount now, but again, this will just be the single version of the class that will exist, and it'll be applied immediately when we create our OS. The next thing that we're going to want is we're going to want a pointer to a logger of type logger, which we're going to set to null pointer initially. Alrighty. So the next thing we're going to want is we're going to want an 8-bit unsigned integer called the exit code, and we'll set that to 0 by default. So the exit code is fairly self-explanatory. We're going to write some getters and setters for it, and all it's going to do is when our application quits, we want to be able to specify an exit code to return in case it's a success or that something failed within the application, and we need to return that error type because something went wrong. So that's the reason that we have exit code set there. We want a uint64 timer frequency, which is set to 0 by default, and another one, which is timer offset. These don't necessarily need to be stored as 64-bit integers, but for the sake of being safe about it, we are going to be storing them as such. The timer frequency simply says how many ticks happen per second. And the timer offset is how many ticks have occurred since the start of the application. The timer offset is how many ticks have happened since the start of the application. So we want to know how far off our timer is going to be set, because when we query to get our delta time, there's going to be several seconds at the time of the application in between us hitting the main entry point, which is registered by the application, and us actually getting to the point where this timer offset is applied. And so we can start calculating how long the application's been running for. So now that we're done with all of our private variables, we're now going to move on to our functions. And of course, the first one is going to be a static pointer to our OS, because we always want to get the singleton that we're using here. The next function is going to be getting the exit code, and that's just a simple getter and setter function, as shown here. And of course, we will want to get our timer frequency as well, because we'll want to query that every now and then for application. And these are all of the non-virtual functions that the OS class will have. Next up is a whole bunch of OS virtual methods. So these are methods that we don't want to implement in our base OS class, but of course our Windows and Linux implementations do want to implement them, and we use the OS class as a virtual layer here to get those. So they are as follows. We have our first list: alerts, prints, print error, printer, and so on. We also have our most important methods, of course, those being our initialize and run functions, and of course our constructor and destructor. And in terms of how those are going to appear in our C++ file, which we will now create, it's a relatively simple file without that much explanation really needed, because again, it's very basic. So I'm going to paste it in as is. And all it is returning the OS singleton, getting the exit code, setting the exit code, setting the singleton, setting, just constructing and destructing and all of that lovely stuff. So there is another class that is going to act as effectively a virtual layer on top of our OS class. So this will be our DisplayManager class, and the reason we're having this differentiation between OS and DisplayManager is because some functions are going to be very specific to display-related stuff, and some of them are going to be more specific to just the general operating system. And depending on whether a function is directly correlated to one or the two will determine which file it goes into. That being said, all we need to do under our OS folder is create a class called DisplayManager.h. We're going to pragma once. And then we're just going to include our type defs and our error macros. And then we have the class itself. So display manager. So in terms of the things that the display manager is going to own in of itself, there's just only really one thing, and that's of course the singleton. There's not a lot else that this class really needs as of the current implementation, since all we're doing is creating a window and then getting rid of it if it exists. But of course, all the window implementations are going to exist in the extension of the DisplayManager class. So we have a couple of public variables before we actually get to the functions, and these are as follows. I don't know why they formatted weirdly like that. But effectively, all they are is our singleton class, a constant definition for an invalid window. So when we're creating windows, this is sort of a thing that exists for when we want to be creating more than one window in the future. I have it just set up here so far that it is an ID that exists, but we won't really be using it outside of a couple of functions. But the idea is that because a unsigned integer can't have negative numbers, it wraps around to being 255. Of course, most applications won't be running 255 windows, so this should be okay, but there is a chance that might be a problem in the future. And we just have an enumeration here of the different kind of window notifications that we might get. And in our current implementations, we're only really going to be using this one because we don't really care about a mouse entering or exiting just yet. However, where that will be used is in a couple of our functions. So the first few functions in this file are going to be as follows. So notification callback is effectively designed so that whenever there is a notification or an event that happens within a window that needs something to happen within other systems that we don't want to directly call from within this implementation of our class, the notification callback will delegate the appropriate responses to whatever that is. And there's a couple other functions here that we'll also be having. So aside from creating and destroying windows, they're fairly self-explanatory. There's processing events, which I'll get into. There's swapping buffers. This is an OpenGL thing. I won't really go over it much, but it will be relevant when we move to making OpenGL. And there's also finalization, because there are some things within this class that we all want to finalize, i.e. clearing windows and so on and so forth before it's destructed. And with all those put out of the way, we can just create the DisplayManager.c++ file. And again, this one is going to be fairly small. Since we only really have 2 default functions that actually exist, or 3 non-virtual functions, they're going to be as follows. We just declare our singleton in this class here. We declare the notification callback, so this is all it does. What it will do is just notify to destroy the window if the method exists, and it sets the singleton whenever it's created and doesn't really do any destruction of that. So onwards to our first Windows implementation. Next up on the agenda is writing the actual implementations of both of these classes. Now, if you've been watching this video so far just to get an idea of what the base classes look like and you want to follow along with the Linux video, now's the time where you can just skip back to that video, because this is the point where we should have everything set up prior to that video, and we will now just be focusing on the Windows implementation. That being said, if you are following this video and you are working on Windows, please continue watching. So the next part we're going to be doing is we're going to be creating our folder for this, because we're not going to be having our platform layer under core. We're going to have this under platform/Windows. So we're going to name that just that. I'm going to go here. We're going to name it Windows. And while we're here, we can also create a file folder called Linux. And this will just be where our Linux versions would exist when we go and do that in the later videos. Now, under Windows, we will normally create a couple of files, and these would be our OS DisplayManager classes. But there are a couple of miscellaneous files, well, one miscellaneous file that we need to do on the Windows side that we'll also do on the Linux side that we need to get out of the way first. That being our logger class, because if you remember earlier in the video, we've now refactored our logger to be extended from. And what that means is that now we are going to extend it so that we can have some custom Windows-specific attributes applied to a logger. So under here, we're going to create a new file, and we're going to call it loggerwindows.h. And we are always going to pragma once and include our typedefs. And now here we're going to be doing something that we haven't done in other parts of our code just yet. And that is we're going to be writing basically an if-def. And that is #if platform windows. And we're going to copy that. And we're going to not do that. We're going to #endif and do a comment there, just so that you know that's the end of it. So here we have a preprocessor definition that we haven't really done before. And this simply says that if the definition platform windows is found, then we want to include all of the code within these 2 lines of code. Otherwise, we just won't add it. What this means for us is that when we go to compile our engine on Linux, all of the code in between here won't be included, which will mean that none of the header files will attempt to be looked for. None of the classes will be compiled. It won't try to do symbols to things that don't exist. It can't load function pointers. All of the functionality that exists in the Windows-specific implementation will not be present. The other thing that we want to do under here is we want to include core-io-logger. And this will just include our logger class so that we can extend it here. So here we're going to create a class Windows logger. It's going to be a public logger. And it's only really going to have 3 main things, or 4 main things, I should say. And these are as follows. So here we have the first thing, and this is can use VT printing, which I'll get onto later. And then we have our overridden methods. So as you will tell, this is our log v and this is our log error. And without any further ado, we are going to go and define these in our source file. So we'll create logger windows.c++, and we're going to include logger windows.h. And again, we're going to do the preprocessor definition of platform Windows. First off, all we're going to do is we're going to create our class constructor, and that is a Windows logger. Windows logger here is that in this instance of the class, we'll set can use VT printing to use VT. And now is probably an excellent time to explain what VT printing is. So VT printing stands for Virtual Terminal Processing. And what that means is that on some builds of Windows, notably the very old builds that we probably won't really be able to support with most of the stuff we're trying to do anyway, it does not support using ANSI escape codes. If you're wondering what an ANSI escape code is, it's effectively a set of characters that you can define in a C string that when printed to the console will change some of the text attributes. So that's how in consoles you can get bold text, you can get colored text, you can get underlined text, you can get highlighted text. All those sorts of things are ANSI escape codes. Now you can get these same effects with Windows' own implementations, but for the sake of making some of our code a little easier to read, we're going to be using these escape codes in certain places. So under the ifdef, we are now going to want to include some Windows headers. And before we actually include that, we're going to be using a very fun macro that Windows gives to us. This is the Win32 lean and mean macro. While it's a very amusing name, but what it means is that whenever we include windows.h, ignore the fact that it's doing the capital W, you want the lowercase one. What this means is that if this is defined, it will only include strictly necessary files for a Windows include, because normally when you include windows.h, it has a whole bunch of things that can really make your executable size very, very large, and we don't want that because we're only using it for a couple things in this file, so there's no point including a whole bunch of Windows includes if we're only ever needing a couple. So we define it as lead and mean because we only want the strictly necessary includes. But from that list, we're going to want to also include stdio.h because we're going to need it for some of our input-output, as you can guess. And we're going to want to include string.h as well, which eventually we could replace with our own string library, but for now we are going to be keeping it here. So the first function that we're going to have is our log v function, and I'm just going to show it right here, and I will explain it as we go through. So I kind of give a brief reason here, and this is just to understand it for most people wanting to read the documentation. It doesn't necessarily always appear because we're not normally logging. We don't normally highlight it as the Windows logger because we're normally going through the virtual methods, but whatever. So this is an example of what VT printing does not do. So down here, we have defined what an escape code will normally look like. So you'll normally have the characters \033 and then an open bracket, and then it will want a number. So normally here, 91 or 90. And then you want m, and then any string that you put in there will apply that text attribute here to that string. And then here we call this to 0m, and the 0 just means that it will reset it back to the default, which is the normal text that you'll get whenever you print something to the console. However, if that isn't supported on whatever system we're using, which is the case sometimes, we then instead query for a std handle, and we use Windows console text attributes instead. So here, if there isn't a console or it's an invalid value, then we just call to the logger to normally go. So if we can't, for whatever reason, get a handle to the console, then we just call to a static logger to log something. One warning that you might want to have later into the application is that if we decide to start shipping builds where we don't have the console appear, then this might become a problem. So we'll have to find ways to circumvent that later on. But otherwise, if you did find the console, then it will just set a color attribute. One prints a red color, and this prints like a cyan color, which is quite nice. We then set the console text attribute. Then we just call to the standard library to print the message from the message and the arg list, because in log v we're always passing the argument list. Then we call to fprintf, which also prints to stdout and prints a new line character. And then here we set the console text attributes again, and that will just set the blue, green, red, will just set all of them back to white, which means that it will set back to the default value. And that's our way of making sure that they set properly. And that's effectively how the virtual terminal processing works. Otherwise, we need to do some other things. And here, this is where we create a buffer. And max buffer length, if you remember from way back when we did the logger class, this is set to 32,000. So this will allocate 32 kilobytes of memory. We zero out the entire buffer. We then print whatever console message we have into that buffer. And then we call to fprintf again. And because fprintf here determines a file, a format, and then some variadic macros, we then want to determine if it's an error or not. So if it is an error, we print a std error. Otherwise, we print a std out. And then it formats this error so it gets the color that we want. So if it's an error, we want 91, which is a bright red. And if it's not an error, then it's just 90, which is a dark color. It's a black, I believe, but it's a visible black. And then here, because the string is after that, it will format in the buffer. And that is printed to the console for all of us to see. Anyway, next up in our function list is the log error, which I'll show as follows. All it's doing here, if we can't use the virtual terminal processing, we don't do anything special for error messages, even though technically I've looked and we could do something. So what we do instead is we just call to logger to print whatever message it is in the details as errors, and then here it prints that as regular text. And because I'm changing how I want to do this, because I'd like to change my mind a lot, I'm also going to swap around file and function here, since I wanted it so that file prints and then the function, then the line. However, if virtual terminal processing can be used, then we can get some wonderful messages. So when I introduced the error type thing, I didn't normally have it formatted in here, and maybe one day we'll go back and make sure that error type is chosen. And that should also have a space there. But here we just declare the color value and the console message. And then we just loop through all of our different error types that we declared earlier in the video. And it will set them to whatever version that we have. And then we make some calls to log f. And initially we set it to true to say that, yes, we do want this to be logged as an error. And here we specify the color value, because that's the first thing we want to format in, which is a brighter version of, which is a nice bright color normally. These are all vibrant colors. The console message, so the message that we want to print. So if it's an error, warning, debug, or shader error. Then we print the color value -60, which in the case of the ANSI escape codes just brings it down to a darker tone. So for instance, the color value here for error is a bright red, and 31 is a much darker red, but that way you can discern between whether it's telling you it's an error or not, and then what the actual error is. And then, of course, as with everything else, we print in our error message and the error details. And then we call to log f again, just to log the next line, which contains our file, function, and line, as some detailed information for us to know where the error occurred. And that is pretty much everything in this file explained. There's a lot going on here, but ultimately it is relatively simple. And now that we've got that out of the way, we can move on to our OS class. So under the Windows folder, we're going to go and create a new file, and we're going to call it OS Windows. And in here, we're going to pragma once. We're going to include our core typedest.h, And again, if platform Windows, or you can spell Windows, and then you just want to end the if. So, and then under here, we're going to include core. So include core os os.h, because of course we are going to be setting up our implementation here. And we're also going to want to define Win32 lean and mean and include the Windows header. Normally, I wouldn't want to include the Windows header in a header file, but we need it for one specific part of this class that can only exist in the header file. So I'm including it here anyway. But then under that, we're just going to write class OS Windows as a public OS. And within here is where the rest of our class definition is going to go. So under here, we're only ever going to have one private variable, and that is as follows. We're going to declare this area as private. I'm going to call this an H instance, underscore H instance. So all an H instance is it's just the instance of the application that is running. So if, for instance, two windows on two separate applications are trying to register a class, normally it would throw an error because you're trying to register two windows with the same name. But because we have the unique instance modifier for each process, Windows knows that it's all good. So under here, we're going to have all of our override functions now, and they are as follows, as you will remember. So again, we have alert, print error, print get current time, usesec, and get OS running time. And then beyond that, we have just a couple other methods. You'll also remember that we have initialize and run. We also have a non-virtual method here, which is get H instance. And all this will do is literally return the H instance of this class. We also have our class constructor and our class destructor, and it takes H instance as an argument for it. Alrighty, that's all of the header file done. Now we can go and write the rest of the file. So again, oswindows.c++, include oswindows.h, hashtag if platform windows, end if, then we're going to want to include our logger windows, and we're going to want to include our our core os DisplayManager.h. So as you remember, the first function on our list of functions is our alert, and that is as follows. So all it will do is it will just create a message box with a given message that we've input with a given title, and it will have an exclamation mark, and it'll have an OK check mark. And Windows does all of the rest of the handling for an alert box for us, so we don't have to do anything. Then below that, we have our three print functions. First of all, we have print, which is, again, all it will do is call to our logger to virtually log whatever messages that we have. And here we call to if the logger already exists, because in some cases, specifically right now, we haven't declared the logger to be created at any point. So it can't log any messages virtually because this will be set to null pointer and it's pointing to nothing, so it can't execute the function. But otherwise, it just calls to this to go through our loggers and log. And then again, it does the same kind of thing for logging an error. Because here we have declared the error type enum in our error macros, we have to typecast it back to the logger error type so that it can be handled properly. But otherwise, it will just act pretty much the same. And we do the kind of the same thing for print error. The difference between print error and print error is that this will just flash an error as one string highlighted in that color, rather than here, which is a more formatted error message, which is designed to be used when we have a problem with our code that needs to be addressed more seriously. Below that, we have a couple other methods. You'll remember these. They are our current time and our OS running time. So here we want to get the current time. The query performance counter function, it always expects a type large integer, which is normally two unsigned 64-bit integers piled together that it can then refer to two different parts. But in this case, we just want the first part of it, which gives us the number of ticks. So we just query the performance counter like so, and it returns the appropriate number of ticks. And then we call to get the OS running time. This will get the, as you can expect, the running time in seconds rather than in ticks. The USEC here means that it has it in microseconds. So that is 10 to the minus 6 seconds. And this would simply return the time as a double, but the double will be in real world units. So this will normally return, say, 5 seconds when the application's been running for 5 seconds and so on and so forth. And the way we calculate that is we get the current time and we take the timer offset, which you'll also notice hasn't been set yet. We'll get onto that. And we divide that by getting the timer frequency, which is also something we haven't set yet, but we will do that momentarily. Speaking of that, this is as follows. This is our initialize function, and it's pretty much going to do all the things that I said we were going to do anyway. So first thing it does is it checks if our H instance has been set. If it hasn't been set, then we want to set it to the current module handle. And when you pass null to module handle A, it will return the module handle to the current application. So that is how we do that. And again, we query the performance frequency this time rather than the performance counter, which we set to timer frequency. Timer frequency, once again, is an unsigned 64-bit integer. So the first 64 bits of the number are written to wherever that is. And the timer offset is set to the current time USEC, which we just query pretty much immediately into the application. So that way we don't have to do any of the changes here when we're getting our OS running time. Next up, we have the run method for the OS Windows. So I'm just going to write this out properly. So this is, of course, OS Windows run. And all it's going to do is while true, when you've spaced it out correctly, it's going to call to the DisplayManager, get the singleton, and we're going to process events. And that's all it's going to do for now. We will go back and change this, but for now, that is all we will want to do. So the last little bit is just our class constructor. So OS Windows. We pass the H instance. Again, we set that in code. We then want to get a handle to our std out, which we do by calling to get std handle and call to std output handle. We then want to create a uint32, so an unsigned long of DW mode. And we just want to query the console mode here. So get console mode to h out and get DW mode. And this will effectively fill this with a certain number of bits to let us know certain features about the console. So then here we're going to call DW mode. We're going to or equal it against enable virtual terminal processing, not input. And if that bit is not yet set, we'll set it manually. And here we call to use VT, which is equal to set console mode to the handle out and to DW mode. And then here we're going to set our logger to be equal to a new Windows logger with useVT as its class construction argument. The way we have it set up here, the reason we do this is because if this returns false, that means that we can't use virtual terminal processing because the flag cannot be set properly. And therefore that means that when we pass it to the logger, we can't use it here anyway. And all that's left to do now in this class so far is just to go to the OS Windows, and we're going to make the destructor. And all that's going to do is that's just going to delete the logger. And that is all of this class done. So now we can move on to one more class before we start setting up the final things to put our main loop together, and that will be our DisplayManager class. So one last time under Windows, we're going to go here, new file, and we're going to call this DisplayManager Windows. .h. I'm going to pragma once, include our type defs. Again, if platform Windows. You should be very used to the process by now because we've done it so many times. And under here, all we're going to include from the rest of our code is we're going to include core-data-event.h. But we are going to want a couple of Windows headers this time. So we're going to, again, define Win32, lean, and mean. We're going to include windows.h. I'm going to specifically need windowsx.h next, which we need for a couple of input things. There's also another thing that I have forgotten to include that I really should have noticed very quickly, and that is that we are going to need our display manager. So include core os DisplayManager.h. So now we're going to go and create the class. So we're going to declare class display manager windows as a public display manager. And under the private section, we are going to declare a couple of things. So in order to prevent having to constantly refer back and forth with the OS Windows class, we are going to declare our own H instance here. And I don't know why I haven't got it set up as to be not being null pointer in our OS Windows, but we should probably also do that as well, since otherwise it can just start writing to invalid memory. And we are, of course, setting this up in a class so we can have defaults. And then below that, we're going to set up our own struct. That is a struct of window data. Within this struct, we're going to have a couple of things. The first thing we're going to have is we're going to have a uint8 ID. We're also going to have an hwind. We're going to have an event of type window notification, uint8. As a notification callback, like so. And then we're going to have a uint16 of x, y, width, and height. And I'll explain very briefly. So in this class, the ID simply refers to the Windows ID. At the moment, this is only going to be set to 0 because we're only going to have one window at the moment. The hwind is Windows' internal handle to its window, so we have to keep it within our window data. The event notification callback is how we are going to call to notification callback in our base display manager. And then the x, y, width, and height simply refer to the x, y position of the window, their width, and their height. So of course we're going to need to hold this somewhere, and that is why we're going to have a window data pointer to window, and this is going to be set to null pointer by default. And this is going to be how we access most of our window data. Now, next up, we have all of our public functions. So they are as follows. So once I fix the formatting, we have our window proc, we have our create window, and we have our destroy window. By default, Windows doesn't actually support having the window proc declared inside the display manager class because non-static functions can refer to multiple instances of a class, and those function pointers often get moved around. So we're going to have to declare a global window proc at some point, and I'll get onto that in a moment. We also then have our create and destroy window functions, and as you can imagine, these are just to give the name, the position that we want to appear at, the width and the height, and it returns the ID because we want to know what window we're dealing with. And the destroy window is just destroying it of a given ID. Then we have our second half for all of our display manager functions, and they are as follows. So we've already been over process events and swap buffers and finalizing. For some reason, I have a finalize function but no initialize in this class, and I have an initialize but no finalize in my OS class. So maybe one day I'll go through and make sure that those are properly dealt with. But otherwise, that's everything we're going to need here. So let's dive back into doing the display manager source file. So here, display manager windows.c++. We're going to include display manager windows.h. Again, if platform windows, and if. We're also going to want to include OS Windows here. First things first is we're going to need our global scope windproc, which I mentioned earlier. And all that is going to be is a very rudimentary declaration here. So all we'll do here is we get a handle to the display manager windows, and we statically cast the display manager to a display manager windows, and that way we can interact with the functions that we have in here, namely this windproc function. And if the display manager does exist, then we call to windproc. Otherwise, we just return def window proc because we don't have anything that can handle our manual overrides. So the first function that we're going to declare here, rather than doing our windproc first, we are instead going to do the rest of our display manager stuff. And that is, of course, our create window class. So I've got a little bit of information about it here. I'm going to return a uint8 of display manager windows, create window. Of course, a const char p name. A uint 16x, uint 16y, uint 16 width, uint 16 height. Well, that's a uin. That's meant to be uint. And the class is going to go as follows. So the first thing we're going to do is we're going to declare an LPC string of class name. And this is just going to be equal to Victoria engine window class. Just one little thing to note about window classes. Since we want all of our windows to go under one window class, it's normally wise to register one class, and then all of our sub-windows with unique titles go under that so that we know which class we're dealing with. However, in order to make that more streamlined with what the game is going to be called, we want to look in at some point later down the line of creating our game's title as what we're going to call our window class, so that the window class formatting makes a little bit more sense. Of course, at the moment, we're not creating any games at the moment. We're trying to get to that point. So for now, we're just declaring the create window here in our create window function. But at some point, we probably do want to move it to somewhere such as the class constructor, where it can actually be called and created properly. So here, we're going to call to window class A of WC, and we're going to zero out the struct, since most of the data here can be zeroed out. The first thing we're going to do is we're going to tell LPFN windproc to be equal to the global scope windproc. And for those of you who aren't aware, that is what these two colons before the windproc means. If I was to just do this without these two here, it will try to register it to a type of, as it will tell me here with this error, of display manager windows as a pointer to this, when it wants to be to just an entity of windproc that is in the global scope. So that's why we add the global scope here, and that's why this global scope one here exists. So then we just want to set up the H instance. So that's set to H instance. We then set the class name here to class name. And then we set the cursor, the H cursor, to load cursor of null IDC arrow. And effectively what this means is that we want to manage the cursor ourselves. So if we were to not fill out the H cursor parameter, the window would just start having a constantly loading symbol because it would try to load its default cursor here. But since we want to manually set the cursor, we want to be able to hide it, be able to show it, be able to change what type it is, all those sorts of things, we declare the H cursor like so. And then it wants some style points. So we need a couple of things for our window to do because we need later functionality. So those are going to be as follows. So csdbl double clicks, and CS own DC. So CS double clicks, as you can imagine, just means that the window can handle double clicks, and they will be processed as a separate event, so you can look for those. And own DC refers to owning the device context, which is when we go to creating our OpenGL context, will become very relevant. But of course, we're not talking about OpenGL at the moment. So below this, once we've done all that, we want to register our class. So we check if register class A has failed. I'm going to pass the memory address of our window class. And if it has, then we're going to want to do a couple of things. First, we're going to want to bleat about it. So we're going to pull up a message box. And the interesting thing about message boxes is that they stop the entire thread that they're running in. So until you close the message box, this function won't return invalid window ID. So you'll have plenty of time to react to the application saying something's gone wrong before you have to do anything about it. Then we're going to want to call to window data of new win. And we're just going to call to new window data. And that will effectively act as an allocation on the stack that a new window has been created. So within this new window, we're going to go new win. I'm going to set the hwind to a new window. So we're going to call to create window exa. And we are just going to fill it up with a bunch of arguments. So another quick subnote that I want to make that I haven't really mentioned in the video. In the Windows API, they normally offer you two kinds of functions. They offer you an A version, a W version, an EXA version, and an EXW version. The difference between the A and the W versions is that the A version will expect a UTF-8 encoded string, so a const char, but a EXW version will expect a wide char version of the string, or a W char, and that is normally 16 bits, I believe, or 32 bits, one of those two on Windows. Since at the moment we're not dealing with any characters that are beyond 16 or 32 bits, since we're only really dealing with the assumption that everyone using our engine can write in English, this isn't a problem. However, if we want to move to making, say, localizations or making it internationally available, then we'll want to look at implementing that, and we'll have to move from using A functions to using W functions. As for the EX part, this simply refers to an extended version of the function that you're looking at that just offers more options for customization that you wouldn't normally have. So for instance, in the window, it gives us a little more control over certain parts of the window that you wouldn't normally get. Anyway, with that out of the way, we can now fill in some of our information. So the first thing we're going to do is we're going to pass 0 as an argument. This is to the extended style. We don't have any extended style. The first thing I want is I want our class name. So you pass class name to that. You then want to pass the name of the window, so p name. It then wants some style things. So here we're going to call ws overlapped window and ws visible. Overlapped window simply gives you your caption title, your system menu, a frame and a minimize box and a maximize box. So as you'd expect in most normal windows, if I look at my own screen, that's giving me this title bar, this minimize box, this maximize box, this close box, and it'll give me a frame around the window that I can work with. It'll then ask you for your X, Y, width, and height, so you can just pass those in as is. Then it'll want a parent. Since we're not creating any sub-windows, we're just going to pass null here. It'll then want a menu. We also don't want to pass a menu here, so we'll pass null. It'll then ask for the H instance, which we've already set, so we can just say H instance here. And then it'll ask for LP params, and again, we don't want to pass anything there. And that is this function fully entered. So if for whatever reason that function has failed, then we want to check that by going to new data or new window, hwind, not height, hwind, and checking if it's equal to null. And here we're not going to bleat about it, but we're just going to return invalid window ID. And otherwise, we're going to want to set the new information about our window. So new win x equals x, new win y equals y, new win width equals width, new win height equals height. I can spell height. Then we're going to want to attach our notification callback. So new win notification callback.connect notification callback false. And then we're going to set window to equal the new window. And then we're going to return new win.-id, which, if I remember correctly, has not actually been set. So we're just going to give it a temporary value here of new win ID equals 0, because we are, of course, expecting for the ID to simply be 0 because there's no other windows being registered at the moment, which is also why window is not being deleted when it's being overridden, which is something that we may have to do in the future. With that monster of a function out of the way, the next thing that we have to do is our destroy window class. So again, the void DisplayManager windows, destroy window with the ID passed. And if the window ID is equivalent to PID, then we're going to want to destroy the window. Now, because of the way we're currently calling this function, it will not free the window. We're going to do that in the finalization. Effectively, we're just destroying the hwind. We're not actually doing anything else to the window at the moment, but we probably should in the future. Next up, we're going to look at processing events. So there's a comment here. I can get rid of it because I'll explain it in a moment. And essentially, all this function does is the first thing we do is we check if the window doesn't exist. Of course, if there isn't a window, there's no events that we can process. So there's no need to do any of the event processing, of course. However, if that is not the case, then we're going to create a new message structure, and we're going to peek at the messages, we're going to translate them and dispatch them. So the important note I have about peek message is that, so originally when I was writing the engine, I was using get message instead of peek message. Initially, this doesn't seem that important, but it's a very important thing to know because get message waits until a window event is happening. This is fine if you're running something like a rasterizer or something of that nature where you need to wait for an event to happen. But since we're trying to render things constantly and we don't want to wait for user events if the user's idling, we just want things to keep happening, it would cause the while loop here to just stall because there were no events being passed. Nothing was happening until you do something like moving the cursor or moving the window around, moving the cursor in and out of the window, typing in the window. All those sorts of things would cause events to happen when we want our window to be updating regardless of whether events are happening or not. So this is why we use peek message instead. Peek message just looks at what's in the event queue. If there's no events, it will just skip this whole process, but if there is an event, it'll translate that message, it'll dispatch the message, and it'll go back again. It'll see if there's any extra messages that have been added. Keep doing that, rinse and repeat over and over and over until the event queue is empty. So next up is swap buffers, and I'm just going to declare that here. Swap buffers. And we're not actually going to do anything in the function at the moment because, again, as I mentioned, this is relevant to OpenGL, and the code for the OpenGL stuff that we need to do here hasn't happened yet. So we're just going to leave this function empty for now, and we'll come back to it when we're a little bit later into the application. We've done the Windows side, and we're actually ready to start putting OpenGL functions in. And just before we do anything else, we also need to do our finalize. So again, so if there is a window that already exists, then we need to call to destroy window. We then want to delete window. So use the delete word on the window. And then we set it to equal to null pointer. And that's all we need to do there for now. And now there is one last function that we need to write. And that is lresult DisplayManager windows windproc. And rather than do all of the arguments, I'm just going to copy them in because they're fairly lengthy. So this is effectively where our set of processing events need to go. Because if you remember here, translating and dispatching the message, all that will do is it'll take the message, it'll say, okay, well, this is what it means. Then we need to send it to whatever function that is, well, window procedure. And we've registered it to this, which then calls to the DisplayManager windows of our current singleton to get the window procedure. So it then calls into here. And this way we have a little bit more control over things. We can also use DisplayManager specific variables here, which is why we chose it to do this way rather than using the global scope one. So the first thing we're going to do is we're going to get a uint8 of window ID. And we're going to set it to invalid at first, simply because we want to make sure that we're doing the right actions. The first thing we're going to do is if window exists, so if there is a window registered, then the window ID is set to window.-id. And then the rest of the code is going to exist in one massive switch statement. So we call to switch of umsg. And all of those will exist in here. Now, before we go and fill that out, we are just going to do the last return. So if none of our messages were handled in the US in umsg, then we just want to call to def window proc and pass in the hwind, umessage, wparam, lparam. And what that means is that any event that we haven't managed within our own iteration here will get managed by default by Windows so that we don't have to declare a bunch of functionality for things that we're not doing. And at the moment, there isn't a lot that we're going to do in this class, but there are a couple of things that we do need to handle. So the first one is case wm close. Of course, when the window requests that it wants to be closed, we need to do something. So here we're going to call to window notification callback dot fire notification wm window close. I'm going to pass the window ID. Then we're going to call to the OS, get the singleton, set the exit code to be 0. As most of you should know by now, an exit code of 0 means that the application has successfully exited. And of course, if this event has been fired, then that is the case. And then all we're going to do here is we're going to return 0 just to let the DisplayManager or just to let the Windows API know that we've dealt with the event manually and that they don't need to do anything on their side. Then the other event that we're going to be dealing with is wm destroy. And all we're going to do here is we're going to call to post quit message 0. And we're also going to return 0 to let Windows know that we have handled this event successfully. Now, there is a whole bunch of other things that you can do inside a window, such as resizing, input, and so on and so forth. But at the moment, we don't handle any of those because we haven't got those systems set up, and later down the line, we will set them up. But for the moment, this is all that we're going to be doing in our window proc class. And that, ladies and gentlemen, is actually this class now done. And that means that the entirety of our platform layer is now set up. Now that we've got all of our code set up to actually do the platform layer stuff, we now need to actually manually create the entire OS procedure, load all the functions, do all of that sort of stuff, and then be able to have our main loop work. So the way we're going to be doing that is we're going to be going to main, and we're going to create a new file under here, and we're just going to call it main.h. And in here, as usual, pragma wants include type defs. And all we're going to do is we're going to declare a couple of functions. The first one we're going to declare is a bool iteration. And the other function we're going to do is going to do void set should quit bool p value. And inside our file, just below here, we're actually going to strip all of this out. And in fact, that goes to most of it, aside from include main.h. Below our int main here, we're going to call the bool iteration. So within iteration, we are going to declare one thing, and that is return should quit. And this is declared, but all we're going to do is going to go up here. We're going to go to static bool should quit equals false. And we're going to set should quit. So below here, or we should probably bool p value. And then remember that you actually need a type, so void. And within here, we're going to set should quit to equal the value that we passed in. And all that means now is that we'll have a way to call into our main loop to say, okay, we need to stop processing. Something's happened. We need to leave, basically. And we actually need to go back a little bit and do this in a couple places. The first place we're going to go is we're going to go to our display manager. We're going to go below here. I'm going to include main-main.h. And right here, we're going to say set should quit to true. Because we've just set the exit code, we want to close the window and we want to quit out of the application. Of course, you don't want to be firing this event normally in this place. This really should be something that's handled at the end of the loop with certain events that are put into our iteration class so that the should quit variable is set properly. But for now, we're just putting this here so that we know that whenever a window wants to close, the application wants to close as well. And within here, we're going to include a couple of other things. Since we're just trying to keep this basic for now, we're just going to include our OS windows. We're also going to include our DisplayManager windows as well. And below the should quit, we are going to declare a static DisplayManager. And now we're going to go and write our main application loop. So first we're going to do OS Windows, OS, passing null pointer. We're not actually going to give the module handle at the moment. We're then going to call to os.initialize. We're then going to call that display manager equals new display manager windows. And then we're going to call to os.run. Then we're going to display manager. We're going to just call to display manager itself. Finalize. And that's everything we need to do. There's another place that we need to change some code, and that is within here in our main loop. We want to say that if iteration, then we're going to break. And when we go back up here, we're going to want to include that from our list. So include main-main.h. So what that means is that by default, iteration will keep calling over and over and over again. But if it returns true because we've set our parameter to quit, then it will return true. And that means that, okay, well, we want to boot out of the application. Now, one thing you'll notice here that we haven't done is we haven't created a window. And we're just going to go to Display Manager here, and we're just going to call to create window. I'm going to call it the Victoria Engine window. And to give it a place of 100, and we're going to make it 1280 by 720 because we are in the modern era. And that is pretty much everything all set up. So now if you hit Control-Shift-B. Right, well, that's a typo on my part. This should be equals as in equivalent rather than being an assignment operator. So if you try to compile again, you shouldn't have any other problems. And there we go. So that symbols error is just reminding me that I missed one really easy function, or two really easy functions. That is our display manager windows. We missed our class constructor. And we're just going to set h instance to be equal to the OS class. So we're going to static cast to OS windows of OS get singleton. And then we're going to call to that to get HInstance. And if that is null, as in HInstance does not have it set up manually, then we're just going to set it to the module handle. So get module handle A of null. And otherwise, our DisplayManager Windows destructor is just going to do nothing for now. Now, if you compile, we shouldn't get any more errors. No linker errors. And if you hit run, this is the moment of truth. You should see that you now get a window and it looks as if nothing is happening. And this is good because we are in our main loop. Events are being processed, even though we can't really see that happening. If we were to, say, print to the console, you get a whole bunch of events occurring. But overall, it looks like everything is working just fine. And if you hit X on the window, you should see that it closes. The application closes all successfully. And we have our main loop set up. So this is a big milestone. What this means is we now have our OS class set up, our DisplayManager class set up. We now have a main loop. We now have events. We can start doing a whole bunch of different systems that we previously couldn't do because of the way we had our code set up. And hopefully you'll also be as excited as I am to start moving on with this project. Now, there is a couple things I do want to note. So obviously this isn't the final form of the project. A lot of these things are going to be changing over time. Ideally, we wouldn't be declaring our DisplayManager Windows here because, of course, when we go and make the Linux version, of course, we won't have any DisplayManager Windows class. So we need to abstract that out in some way. So it's very likely that once this video goes out and the Linux video goes out, where I place some of this, we'll start swapping things around and moving things into their own implementation files. But this means that we are one step closer to getting that triangle rendering. So once again, I do hope that you enjoy this video, and I will see you in the next one. Goodbye.